Assalamualaikum to one and all. Welcome back to my tutorial in high school physics and chemistry. Today's episode focuses on analyzing a pressure volume graph that describes an isobaric expansion and isothermal compression of an ideal monatomic gas. Find out how we apply Charles' law and the first law of thermodynamics in this situation. I enjoin you to stick around, watch and learn. The question is, 1 mole of an ideal monatomic gas expands isobarically from state A to state B, as shown in this graph. It is then compressed isothermally from state B to state C, and finally cooled at constant volume until it returns to its initial state A. So at state A, we are given the volume of the gas equal to 4 times 10 to the negative 3 meter cube. At point B, or state B, the volume of the gas is 8 times 10 to the negative 3 meter cube. The temperature at state A is also given, which is 600 Kelvin. We're also given the pressure on the gas at state A, which happens to be equal to the pressure on the gas at state B, and that is equal to 1 times 10 to the 6th Pascal. At state C, the pressure on the gas is equal to 2 times 10 to the 6th Pascal. And question letter A, what is the temperature of the gas when it is in state B? And question letter B, how much work is done by the gas in expanding isobarically from state A to state B? Based on the pressure volume graph, the gas starts at the thermodynamic state A and proceeds to thermodynamic state B at a constant pressure, and we refer to that as an isobaric process. The pressure on the gas is the same at state A and state B, but the volume of the gas is doubled as it expands isobarically from state A to state B. The work done by the gas in going from state A to state B is just the product of the constant pressure and the volume difference, which is the final volume minus the initial volume. And we say that the work done W is positive when the gas expands, and it is negative when it contracts or gets compressed. Also, we can say that the work done W is positive if the system is the one doing the work, and the work W is considered negative if it is the surrounding that is doing the work on the system. According to the given problem, when the gas is compressed from state B to state C, the thermodynamic process is considered to be an isothermal process, all right? One that occurs at constant temperature. So whatever the temperature of the gas at state B, all right, it will also be the same temperature when the gas is at state C. Notice that during this um, process of compression, or the gas being compressed, there is, of course, a decrease in the volume due to the increase in pressure, right? So at state C, although the volume is less than at state B, but the pressure is higher, right? Now, an isothermal process where the temperature is constant implies that the change in internal energy delta capital U is equal to zero. Hence, based on the first law of thermodynamics, right, the work done on the system, right, um, which is considered a negative work, all right, this amount of work or energy, all right, is not being used by the gas to increase its internal energy. So, because of that, um, the amount of work on the gas will just be equal to negative Q if delta U equals zero. All right? This is based on the formula for the first law of thermodynamics. And negative Q here represents the heat or thermal energy that is given up or liberated by the system, in this case by the gas. So, from a higher pressure but lower volume, all right, that's at state C, the gas is finally cooled at constant volume, all right. A process with constant volume is referred to as isochoric process. And in the graph, the isochoric uh, process occurs, okay, as the gas proceeds from state C to state A, and represented by this thermodynamic path, all right, CA. So, path CA means that the system or the gas is now returning, okay, to its original or initial state, which is state A. And since the gas is cooled, all right, at constant volume, meaning there is no work done by the gas or on the gas, and plus the fact that the pressure also drops. So this isochoric process implies that um, there is a decrease in the system's internal energy. All right? The internal energy, delta U, okay, with work W being equal to 0, delta U will just be equal to negative Q. And a negative Q here means that the gas liberates or gives off the heat or thermal energy. Moving on now to our answers to the given problem. Question letter A. All right. Our first target variable is the temperature at state B. So using the gas law formula, which is actually Charles' law, all right, where the product of the initial volume of the system multiplied by the temperature, all right, or final temperature is just equal to the product of the final volume and the initial temperature. All right, that is Charles' law. Right? So in Charles' law, um, the pressure is held constant. All right, and since our target variable is the temperature at state B, then we can just isolate T sub B in this formula. All right, so T sub B will just be equal to the product of the volume at state B multiplied by the temperature at state A to be divided by the volume at state A. So that when we substitute, all right, we have 8 times 10 to the negative 3 meter cube. That's the value of the volume V sub B multiplied by the initial temperature TA, which is 600 Kelvin. All right, and then to be divided by the initial volume V sub A, 4 times 10 to the negative 3 meter cube. So doing our math, we will arrive at this value for the temperature at state B equal to 1200 Kelvin. And for our question letter B, okay, we are asked to find the work done by the gas as it expands, all right, um, from state A to state B, all right. So we denote the work done by the gas with the symbol W sub A to B. And the formula in determining this amount of work done is just the product of the constant pressure P sub A, all right, by the difference in the volume B sub B minus B sub A, right? Likewise, this amount of work done by the gas can also be represented graphically in this figure, all right? The area of the rectangle shaded green, all right, would represent the amount of work done by the gas. And as we all know, the area of a rectangle is just the product of the length and its width. So, the width of this rectangle represents the difference in the pressure, all right, which is actually just equal to the pressure P sub A, because it's understood that the intersection of the P axis and the volume axis is 0, all right? So when we get that difference in the pressure, it's just actually P sub A minus 0, or simply P sub A. But the length of this rectangle is represented by the change in the volume, all right? B sub B minus B sub A. So, plugging in the quantities into this formula, we will have the work done by the gas equal to 1 times 10 to the 6 Pascal, right? Which is the constant pressure, or P sub A, to be multiplied by the change in the volume, all right? So, B sub B, which is 8 times 10 to the negative 3 meter cube, minus B sub A, or 4 times 10 to the negative 3 meter cube, we get the difference in the volume equal to 4 times 10 to the negative 3 meter cube. In doing our math, we will arrive at this amount of the work done by the gas equal to 4,000 joules, which is our final answer to question letter B. So that's it. We are done. Till the next episode, mabuhay. Alhamdulillah. Insha'Allah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.